Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Distributed Economic Dispatch. Lecture prepared by Engineer Jesús Velásquez-Bermúdez, Ph.D. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. Distributed Economic Dispatch. Distributed Economic Dispatch, DED, is an optimization model in smart grids that seeks to allocate energy generation at the lowest possible cost without depending on a centralized control center. In this system, each generating unit acts as an intelligent agent that makes local decisions and communicates only with its neighbors. Unlike the centralized model, the system is represented by a communication graph, where the nodes are the agents and the arcs are the data links. Important concepts in DED are consensus variables. The key concept is marginal cost. The system reaches the economic optimum when all generators operate at that level. Information mechanism. Agents use a consensus algorithm to estimate the overall miscoordination between supply and demand, based solely on information from their immediate neighbors. Topology. This can be a bus, ring, or mesh network, and the model must be robust to changes in topology, such as link failures or cyberattacks. The overall goal is to minimize the total cost function, subject to power balance constraints and capacity limits. Consensus algorithms are fundamental to the operation of decentralized networks, mainly blockchain networks. They ensure that all network participants agree on the validity of transactions and the state of the blockchain. Without consensus, there would be discrepancies in the data between different nodes, which could lead to fraud and errors. These algorithms facilitate trust between users who may not know or trust each other, allowing decentralized systems to function effectively. Different consensus mechanisms have been developed to respond to the needs of various applications, each with its own strengths and weaknesses. Validate transactions and add them to the database. Prevent double spending and fraudulent activities. Improve network security against attacks. Optimize network performance. Allow decentralized decision-making. There are several types of consensus algorithms, each designed to address specific needs and challenges within distributed and autonomous network technology. Each type employs different mechanisms to achieve consensus, thus influencing the overall efficiency and scalability of the network. Understanding the particularities of each can help determine which one is best suited for specific applications. The most widely recognized types are: proof of work requires participants to solve complex mathematical problems. Proof of stake allows validators to create new blocks based on the power they possess. Delegated proof of stake involves selecting some nodes to validate transactions on behalf of others. Practical Byzantine fault tolerance errors focuses on achieving consensus despite failures or malicious actors. Proof of authority relies on a limited number of trusted nodes to validate transactions. The importance of consensus algorithms cannot be underestimated, as they provide the backbone for the reliability of autonomous and distributed networks. They ensure that all participants maintain a unified view of the network, which is essential for transparency and accountability. These algorithms protect the network from various types of attacks, such as Sybil attacks, where a malicious actor creates multiple identities to take control of the network. The choice of algorithm can significantly affect the speed and scalability of transactions. Therefore, selecting the right consensus mechanism is a critical factor in the design of a decentralized system, because they establish a safe and reliable way to reach an agreement, minimize the risk of network forks, which can lead to confusion, allow the system to function without a central authority, dictate how quickly transactions can be processed, and influence the costs associated with maintaining the network. While consensus algorithms are essential, they also come with their own challenges. A major issue is scalability, as many algorithms struggle to efficiently handle a growing number of transactions. Some consensus mechanisms, such as proof of work, POW, have been criticized for their high energy consumption and environmental impact. Security is another concern, as vulnerabilities in the algorithm can lead to exploitation and attacks. Achieving consensus in a decentralized environment can introduce latency, affecting the overall performance of networks in real time. These challenges require continuous research and innovation in the field of consensus mechanisms. Some problems to be solved are: scalability issues can lead to slower transaction times. Energy consumption is a significant concern for PAL systems. Security vulnerabilities can expose the network to attacks. Latency can affect the user experience during high traffic periods, and continuous improvement in algorithms is necessary for adaptation. The future of consensus algorithms is promising, with continued advances aimed at addressing current limitations. Innovations such as hybrid consensus models are emerging, which combine diverse algorithms to leverage their strengths while mitigating weaknesses. Research on more energy-efficient consensus mechanisms is gaining traction, focusing on sustainability. As autonomous networking technology evolves, we can expect a greater emphasis on scalability and speed, ensuring that decentralized systems can compete with traditional centralized solutions. The development of new consensus algorithms will play a key role in shaping the future landscape of autonomous networks. Hybrid models can enhance performance and reduce energy use. New protocols are being developed for faster transaction times. Research into quantum-resistant algorithms is on the rise. Community governance may influence future algorithm designs, and the integration of artificial intelligence may optimize consensus processes. Consensus algorithms are vital to ensure the reliability and security of real-time networks, such as smart grid networks and blockchains, as they facilitate agreement between decentralized participants, enabling transparent and reliable transactions. While challenges remain, innovation still promises to improve the scalability, efficiency, and sustainability of networks in real time. As the landscape continues to evolve, understanding these algorithms will be essential for developers, users, and stakeholders in the distributed operations ecosystem. In smart grids, consensus algorithms are used to coordinate distributed decision-making among multiple agents, like smart meters, microgrid controllers, distributed generators, without relying on a central authority. They are crucial for distributed energy management, economic dispatch, voltage/frequency control, and peer-to-peer energy trading. The distributed economic dispatch are the future of the new generation of dispatch models, which must evolve towards autonomous and distributed architectures, typical of Industry 4.0. A fully distributed approach for economic dispatch problem of smart grid. In the traditional power grid, power is transported from a few central generators, such as thermal power plants, hydroelectric power plants, etc., to a large number of users, and the traditional power grid focuses on electricity generation, transmission, distribution, and control. Recently, new renewable energy generators, such as photovoltaic systems, wind turbines, etc., have been used to offer an alternative form of electricity production. In addition, the demand for electricity is diversified and the traditional electricity grid is insufficient to overcome the current challenges. Now, the smart grid, SG, is used to improve the reliability of the electrical system by allowing it to be controllable and automated. A fully decentralized solution collects data from each agent and solves the economic dispatch problem, EDP, considering generation limits. The distributed approach contains two stages, both based on consensus algorithms. First, the flood-based consensus, FBC, algorithm is used to share information between agents, and a ring communication graph is proposed, since the agent can receive or send information from or to its two neighbors. Second, the algorithm called L-consensus, LC, based on a consensus procedure is used. The parameter L works as a correction term to satisfy the generation demand equality constraint. The process can be summarized as follows. First, the algorithm is fully distributed. All agents, or nodes, have the same status, this is, no agent is different from other agents in their information and behavior. There are no leader agents, thus the algorithm in this paper not only achieves plug and play but also has strong robustness. Second, in the first stage of the algorithm, a method to collect global information by sharing information with neighbors, can effectively alleviate communication congestion. Flood-based consensus, FBC, primarily refers to an algorithm used in distributed systems and smart grids for multiple nodes, or agents, to reach a common agreement on a specific value or data. FBC is a propagation mechanism that works using the flooding technique, where each node sends the information it possesses to all its immediate neighbors in each round. The stages of the algorithm are: collection, agents exchange system data, such as generation or load units, so that each node has a complete view of the network. Local processing, once consensus is reached on the data, each agent solves complex problems, such as the economic dispatch of energy, locally. FBC is especially useful in fully decentralized systems, allowing to solve non-convex optimization problems and manage transmission losses with high precision. It is used to distributed systems, used to solve the consensus problem, ensuring that all non-faulty nodes decide on the same final value after a certain number of rounds. Smart grids, used for distributed economic dispatch, where generators and loads must agree on system data to collectively minimize operating costs. Leader choice, algorithms like FBC use this logic to choose the node with the highest identifier as the leader of the network. The deployment of sensor technology and smart meters has accelerated the development of the SG. Data communication network infrastructures include wide area measurement systems, WAMS, sensor and actuator networks, SANETs, home area networks, HANs, neighborhood area networks, NANs, and wide area networks, WANs. Different communications media, wired and wireless, can be used for data transmission between smart meters and electric utilities. SANETs can be grouped under a hierarchical structure based on HANs, NANs, and WANs, as shown in the figure. As an alternative to the traditional power grid, the SG can alleviate the burden caused by various energy demands. However, the increase in electricity demand, coupled with the complex and nonlinear nature of electricity distribution, has posed many challenges for the future grid, for example, severe network communication problems, and it is costly and unreliable to solve the economic dispatch problem, EDP, using traditional centralized methods. SG, with distributed energy sources accessing, require distributed approaches to deal with its energy management problems. As an alternative to the traditional power grid, the SG can alleviate the burden caused by various energy demands. However, the increase in electricity demand, coupled with the complex and nonlinear nature of electricity distribution, has posed many challenges for the future grid, for example, severe network communication problems, and it is costly and unreliable to solve the economic dispatch problem, EDP, using traditional centralized methods. SG, with distributed energy sources accessing, require distributed approaches to deal with its energy management problems. Graph theory has been widely applied in many fields, such as computer science, operations research, practical engineering, among others. Graphs are composed of vertices, also called nodes or points, and edges, also called arcs or lines, which denote objects and some kind of relationship. Depending on the direction of the edges, graphs can be divided into directed, or digraph, and undirected. To define the graph, the adjacency matrix is associated with the directed or undirected graph, and with the set of indices that represents the nodes. In digraphs corresponding to smart grids, a single node can be purely energy generator, or purely load taker, or include power generation and loading. The smart grid consensus algorithm. In smart grids, SG, the nodes, including the generating units and loads, can be thought of as a group of n participating agents. The matrix Q that belongs to the positive real numbers in N2 represents a strongly connected graph G between n agents. Agent can define his own subjective parameter probability distribution, and they work together as a team to reach a target values under some constraint conditions. The figure shows an undirected graph that includes 4 nodes. The data is associated with this case. The matrix Q is associated with the undirected graph. Qt is the value of Q, when t is the number of iterations. If t is greater than or equal to 8, Qt is equal to Qt plus 1, implying that Qt has reached a steady state, in the same way that all values of pi are steady state. Equation 4 means that all state variables will converge to a common value after t iterations, which depends on the initial value, and on the communication topology Q. Take as an example the 4-bus network in the upper figure. The lower figure shows an undirected ring communication graph that connect each agent. We choose the undirected ring graph as the communication topology because it is easy to observe the stopping condition in the ring communication topology. Per iteration, each agent receives 2 messages from their 2 neighbors. Meanwhile, each agent sends a message to its 2 neighbors in each iteration. The figure shows the process of collecting data for a 4-bus network. Before the first iteration, each agent prepares its messages. When an agent receives a message, it parses the content and updates the information by adding it to the information it had already received. After each iteration, each agent will check its message. This means that each agent reaches consensus about the power system after m iterations. The classic problem of economic dispatch of electricity systems, including its analytical solution and a fully decentralized approach, is presented in this section. A power system with m buses and n generation nodes is the reference. N less than or equal to m. The total cost is denoted by F and is equal to the sum of the costs of each generator. The essential constraint is the balance between supply and demand. It implies that the total power generated must be equal to the total load demand. This is an optimization problem that can be solved with the Lagrange method. The proposed approach for solving EDO via DET is composed of 2 stages: data collection based on FBC algorithm and optimal solution based on lambda consensus algorithm. In the stage of data collection, agents share information about their neighbors who connect to them in the power system, and parameters including load demand and power outputs that can be generated by generators in their buses. Agents share information and reach consensus about the power network based on FBC algorithm mentioned. In the FBC algorithm, a token is defined to permit agent to send its message to its neighbors in communication network. The token plays the role of transmission permits. Agent with a token can send message to a selected neighbor, and it is necessary to define the communication topology before agent communicating with each other. It is assumed that there is an agent in each bus of the power system. These agents are embedded in the power system and responsible for message sharing and EDP calculating. The algorithm pseudocode for FBC-based data collection is shown in the figure. After completing the data exchange between the agents, an agent is randomly chosen to obtain the Q matrix based on their message. Each row in Q is only related to the number of neighboring nodes. Each agent reaches consensus on its information. Taking the network of 4 buses as an example, if the chosen agent is agent 3, based on its message, we can get the Q and the param vector shown in the text. Note that choosing a different agent corresponds to different Q matrices and param vectors. However, due to the one-to-one match between Q and param, the result will not be affected. The figure shows the flowchart of the algorithm. 4 simulation cases shows the performance of the algorithm. First and second, we consider the cases with and without power generator constraints. Third, the plug-and-play properties are demonstrated through adding generator and load shedding. Fourth, the IEEE 57 bus is used to show the effectiveness of the lambda consensus algorithm on large cases. There are 3 types of generators: Type A, Type B and Type C, correspond respectively to the coal-fired steam unit, the oil-fired steam unit and the diesel steam unit. In addition, the power types and ranges of the generators are indicated, as well as the cost parameters A, B and C. The figure shows the IEEE 57 6-bus system. It contains 6 buses, indicated by a thick line, 11 single lines, and 3 generators, indicated by circle. Ignoring the transmission loss of the line, the generators in this smart grid, SG, are labeled as A, B, and C. 6 agents using Java Agent Development Framework was created. They correspond to the 6 bus, respectively. A ring topology based on bus number was created to collect information from different buses. In the first case study, power generator constraints are not considered. Initial charging demands are 180, 350 and 500 megawatts on buses 4, 5 and 6. The output of the generators, the estimated mismatch, the incremental cost and the total power generated are shown in the figure. The power outputs of each generator gradually stabilize, and the miscoordination between demand and the total power generated is reduced to zero after 18 iterations. In addition, the estimated incremental costs of all generators are trending toward a stable value. The results are: marginal cost equal to $8.99 per megawatt hour, power generator 1 equal to 630.6 megawatts, power generator 2 equal to 293.8 megawatts, and power generator 3 equal to 105.6 megawatts. In the upper left graph, the first generator exceeds the limit of its maximum power output of 600 megawatts. In this case study, power generator constraints were added, using data from the previous case. After 40 iteration, the behavior of the algorithm tends to be stable. The results are marginal cost, L equal to $9.05 per megawatt hour, power generator 1 equal to 600.0 megawatts, power generator 2 equal to 315.5 megawatts, and power generator 3 equal to 114.5 megawatts. In this case, no generator exceeds its maximum output power. Generator 2 uses its maximum power. In this case study, the plug-and-play adaptability of the lambda consensus algorithm is analyzed considering the same power system as in case study 2. The plug-and-play function simplifies the process of accessing the smart grid of the new power generation capacity. In time step 60, the demand for charging on bus 6 drops from 500 megawatts to 300 megawatts. The fourth generator is connected to bus 4 at time step 120. The type of the fourth generator is C. At the beginning, all 3 generators have already stabilized at steady-state values before the load cutoff from bus 6. When there is a power outage in time step 60, the total power mismatch increases from 0 to 200 megawatts, and the system reaches a new balance between generated energy and demand after a few iterations. At this point, marginal cost, L equal to $8.7108 per megawatt hour, power generator 1 equal to 531.9 megawatts, power generator 2 equal to 221.6 megawatts, and power generator 3 equal to 76.5 megawatts. At time step 120, the buses detect a new generator at node 4 and change the bus capacity to operate between 50 and 200 megawatts. Under the new conditions, demand is redistributed and converges towards a new solution. Marginal cost, L equal to $8.6172 per megawatt hour, power generator 1 equal to 498.9 megawatts, power generator 2 equal to 197.5 megawatts, and power generator 3 equal to 0 megawatts. Power generator 4 equal to 66.8 megawatts. The total power generated by generators is 830 megawatts. The simulation shows that the total power mismatch, generator outputs, estimated incremental cost can reach new steady-state values after a few iterations. This suggests that the algorithm can adapt to the dynamic environment of smart grids, which determines its effectiveness. This power system of IEEE 57 bus contains 7 generator buses. The generator parameters are shown in the table. The initial power demands at each buses are denoted, and total demand is 1,250.8 megawatts. The case study includes generator constraints. The generator's outputs are fulfilling the constraints on their maximum output power. After 760 iterations, the system achieves the balance between the energy generated and the load demand, and the incremental cost that produce the equilibrium. Marginal cost, L equal to $22.4461 per megawatt hour, power generator 1 equal to 131.6 megawatts, power generator 2, 6, 9 equal to 100 megawatts, power generator 3 equal to 40.8 megawatts, power generator 8 equal to 460.4 megawatts, and power generator 12 equal to 317.6 megawatts. The total power generated by generators is 830 megawatts. Distributed economic dispatch. Lecture prepared by engineer Jesús Velásquez-Bermúdez, Ph.D. High power. The coordination of two types of models is studied: economic dispatch and unit commitment, and competitive electricity markets, distributed economic dispatch, electricity system and wholesale market optimization models. Make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. High power is a decision support system that has been developed to support the decision-making processes of agents participating in the electricity and/or natural gas markets. High power is composed of a set of optimization models that describe the supply/demand process of electricity and natural gas. From this point of view, it determines the partial equilibrium point of the electricity and gas markets under conditions of economic efficiency. Four models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. High power is built following the principles of structured mathematical modeling, which are specific to optics. Under this conception, software is built by means of layers of equations, which are integrated to build the models, which are part of a decision support system. In the case of high power, it is an economic dispatch model, typical of the electricity sector. The diagram shows 8 of the many models available at high power. Any of the models can be run in their deterministic or stochastic version, making use of asynchronous parallel optimization. Operational planning and unit commitment. A well-known activity in the electricity sector is the coordination of two fundamental models: economic dispatch, or operational planning, DP, and unit commitment, UC. Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Below, we will briefly and partially discuss High's philosophy on the operating models it has used so far in the power sector, which can be used for an isolated smart grid. But with the arrival of Industry 4.0, technological change led to smart grids being considered autonomous and independent networks, which totally changes the modeling paradigm, considering that today there are no longer monolithic electrical systems. Attempting to model a smart grid network with traditional dispatch models is a major mathematical error. First, its size would be unmanageable in data and computer processing. Second, mathematics has changed to adapt to this new era. It makes no sense to use outdated mathematics, and third, it may be most important, it violates the philosophy of the new business and its regulation. All the models and methodologies developed for the electricity system and the wholesale market are applicable to smart grids, when analyzed as an independent system. It's just a problem of scale. Unit commitment, UC, associated with short-term operational planning decisions, such as the optimization of detailed distribution by the hour or for shorter periods, respecting all the constraints of the nonlinear and discrete system. The UC model is a mathematical problem that can be converted into nonlinear non-convex mixed optimization, which implies that it requires a special effort for its solution, since its real-time characteristic does not allow unfeasible approximations for its solution. On the other hand, it is necessary to coordinate the UC model with a medium-term planning, DP, model, which establishes the boundary conditions, in such a way that the state of the system at the end of the UC problem be the same as at the beginning of the DP problem. Below, we will briefly and partially discuss High's philosophy on the operating models it has used so far in the power sector, which can be used for an isolated smart grid. Ideally, a single model should be solved, which would allow the system to be represented in detail throughout the planning period, that is, solving a long-term scheduling problem during periods 1 to t. For complex systems, this may not be computationally viable. However, for not-so-complex systems the alternative could be viable, considering the computational capacity offered by Industry 4.0. For this reason, conventionally it has been considered necessary to resort to the integration of both models, UC and DP. You should consider the implicit approaches involved in such a decision. Based on the vision of the artificial hypothalamus, Building a monolithic model consists of cutting and pasting equations, and thus obtaining the optimal solution, regardless of the type of dispatch model that is appropriate according to the market. The solution of the monolithic model can be realized with large-scale optimization methodologies. The traditional thing has been to divide the process into two models. Stochastic economic dispatch model, oriented to planning activities, and deterministic model of unit commitment, oriented towards real-time scheduling. The coordination of both models is essential for the results obtained for the real generation. The traditional way to approach the problem is to coordinate the two models, solving each independently, offline, so that the office planning model, DP, establishes the boundary conditions of the office scheduling model, UC, which can be interpreted as the optimal planning objectives. This approach may not have a viable solution in the UC, because the differences and/or approximations could lead to the non-viability of the set of objectives established by the DP for the UC. There are two alternatives to carry out coordination. Coordination through economic variables, dual variables or prices. To this end, the opportunity value of inventories is set at the end of the period TCP, or at the beginning of the first period. In this case, it corresponds to the value of the water. The application of this approach should be careful, as boundary conditions should reflect variation in prices between periods, but in general, only a sample of the value of water is considered, at the beginning or at the end of the planning horizon. This can lead to water value profiles, which are far removed from the profile estimated by the DP model, which is never observed in the UC. This approach always offers viable solutions, but they may be far from optimal due to the distortion of the dynamic price profile. Coordination through physical variables, primal variables or quantities. To this end, the quantities of resources to be used and the quantities of industrial products to be produced during the period of operation of one to the same period are established. The inventory levels that must be reached at the end of the period, the TCP moment, are also established. This approach does not distort the dynamic price profile but may not have a viable solution due to the small differences between the two models. Non-feasibility, which can be managed by soft constraints, which introduce penalized slack in the target function, to ensure that the final schedule is close to the optimal target set by the planning. The chaining, or coordination, of models does not guarantee optimality, because there are always at least two alternatives to concatenate two models. By quantities, or primal variables, such as water use, or resource use in general, or by prices, or dual variables, that is, the value of water, or in general the value of resources. Cyclical coordination can produce the optimal solution, or correct unfeasible solutions. The integrated model can be solved using large-scale techniques, such as Bender's partitioning and Lagrangian relaxation. This approach reduces solution time and memory requirements. Operational planning and unit commitment. A well-known activity in the electricity sector is the coordination of two fundamental models: economic dispatch, or operational planning, DP, and unit commitment, UC. Each smart grid requires a specific decision support system that allows the operator to interact with the entire electricity system. Starting from the original electrical system, a wholesale electricity market. Smart grids were advancing little by little, initially seen as isolated systems. Currently, these electrical systems must coexist and interact with each other. The centralized control of the system focused on the development of assets, hardware and software, for the wholesale electricity system. The emergence and development of smart grids generates a distributed control of the system, in which many islands, which initially operate in isolation, must be coordinated. Technological evolution has given rise to total distributed control, in which multiple types of electrical assets coexist and communicate with each other. Smart grids have generated communities of users that consume and generate energy and require a broad control system that unites all the production-consumption cells that the electricity system has. It is a system like the Internet, where the autonomous communities share physical resources and communicate with each other, which gives greater power to the physical system, but requires more advanced artificial intelligence to manage it. Under the concept of OpTeX, Optimization Expert System, the software is built using layers of equations that are integrated to build the models. The current models of dispatch planning, DP, and unit commitment, UC, can be used for current smart grids, making the necessary scale and regulation adjustments. Autonomous real-time distributed economic dispatch. Challenge: modify the traditional centralized economic dispatch through a distributed economic dispatch to enter the Industry 4.0 environment. Solution: it implies that all agents must know what information they need to take from smart metering systems, and what information they must provide to other agents to make their decisions, to keep the end-to-end system on the optimality path. This is possible using asynchronous parallel optimization methodologies. Methodology: in the case of regional smart grids, the process of planning or scheduling electricity systems could be carried out as follows. The connection topology of smart grid networks is developed according to the criteria of a central coordinator, the regulation, and/or the autonomous decisions of the agents. The mathematical models running on each smart grid correspond to the currently tuned models, DP and/or UC, but in general they are the same models that are currently used. The adjustments of the models are related to scale or regulation details. This network does not require a physical coordinator, as the models run independently on each smart grid and coordinate autonomously, and the coordination of the models can be done by prices or by quantities, which will be the consensus methodologies. The two methods of coordination are valid mathematical methodologies, either by prices or by quantities. The system coordinator must choose one of the two. Perhaps it is better that it is regulated, because all smart grids must coexist autonomously and independently in the same region, but following game rules. Coordination by quantities is more complicated, because it is not a variable common to the subsystems. Coordination by prices seems easier and is a well-known rule in economics. Optimal marginal costs, without restrictions, must be the same in all smart grids. This is a consensus scientific rule, which has been well studied and cannot be questioned, since it is not an opinion. This is High's proposal. The solution of the UC or PD problem is independent of the conception of the distributed dispatch system. Within each smart grid, the optimization problem can be solved monolithically or use large-scale optimization techniques, such as Bender's and Lagrange's decomposition theories. Models with different methodologies, or technologies, of solution can coexist. The graph presents a topology composed of two groups of smart grids and a large generating plant, and a wind farm. The approach can be conceived as an artificial brain composed of a network of mathematical models, a model for each smart grid and for each site of large generation and/or consumption. Communication between the algorithms of mathematical problems must be asynchronous when events occur in the system. This can be continuous. For optimization purposes, the artificial brain does not need a coordinator, as the smart grid system acts autonomously and independently. However, in order to function as a technical control and regulatory control, it may be necessary to have a system supervisor. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.